Anytime you make a measurement, in order to make an accurate measurement, you're going to want to make sure that your sensor is calibrated. And calibration is simply applying known inputs and observing the system output. Now one can dive pretty deep into a rabbit hole of understanding what known inputs are. So for example, if I'm trying to calibrate a force sensor, I might provide known masses to that force sensor in a known gravitational field, and that would give me a known force. Now, how I determine that something is actually a kilogram, right, comes back to traceability and standards. And the actual reference of a kilogram has actually changed a lot over the years. And up until very recently, it used to be a chunk of alloy. It's a platinum iridium alloy. You can actually go down the road to NIST and see this kilogram. And very recently, in about the last 5 years, the Standards Committee finally changed it to kind of nature and variance. And mass, for example, is based on the Planck constant now, instead of just a chunk of metal. But different standards are going to have different requirements for how traceable back to that Planck constant standard or that platinum iridium block of metal standard are. So how much I know that it actually reflects what those standards are. But back to the idea of calibration, the basic idea is that I'm providing these known inputs, so various inputs along this F line here, and I am measuring my output of my sensor. In this case, I've called it a resistance. And so I get a number of measurements based on the number of forces that I apply to my sensor. Now, typically one of the challenges is that I don't want to apply 100 different forces to get 100 different points here. So I typically have very few points in this calibration curve. So if I have a linear calibration curve, I'm going to come up with a Y, which is my kind of calibrated resistance, is going to have some Y-intercept plus some slope here. And I might use something like a least squares fit to my data to actually get this curve, to get my two coefficients in this curve here. Now, a more general calibration curve, you just have y as some function of x. But probably 90+% of the time we're actually trying to get a linear curve out of our sensor. In this calibration curve, given that we're getting an output for our input, is also going to get us our static sensitivity, at least valid for the range of data over which we're doing this linear fit in this case. And I don't have any calibration data above this force, for example, so I can't really say that this sensitivity holds above that force. So that's why it's only valid over this particular range of data. Let's look at a quick example of that from some of our own work. So in this case, we're looking at a capacitive sensor. So on the y-axis, I have a change in capacitance in picofarads, and this is effectively a displacement sensor. On the x-axis, I have a displacement in microns. So I'm applying a known displacement, and I'm doing this over different, in this case, slightly different versions of the same thing, and trying to find a linear fit for all of this data. So you can see right here I have some scatter in my measurement data, and not surprisingly that scatter is going to be representing noise. In this case I'm applying a linear fit to this data. It seems to reflect the data fairly well to do this linear fit, at least over this range of data up to about 25 microns or so. And in this case I can also try to get a sense of the static sensitivity of this sensor. By looking at the fact that I'm at 25 microns, I'm looking at about 0.75 picofarads or so. So my K is going to be 0.75 picofarads divided by, in this case, 25 microns. And so I'll be getting approximately 0.3 picofarads per micron. But this is what a typical calibration curve might look like. although often you'll have far fewer points along this x-axis. Right? And that's where you have to be very careful about assumptions around linear sensitivity, for example.